That's it? Yes, one digit. So under what condition? So अगर हम इस abstract problem को, if I kind of solve this abstract problem, this problem and another problem that I'll told you about, the diagonal equation will be solved. Okay? So the way is this actually. So if U is, what do we call it? We rewrite this problem U as a U plus F actually. That is all this. And the argument that I would like to use is what do you call your so-called Banach fixed point theorem. I mean, if you remember the proof of fixed point theorem, okay, there actually we defined an iterative process. Actually, if you remember, we did something like this: that xn plus 1, in some sense, you can obtain it from xnth term under certain transformation. Or you do this all the time in what you call your numerical analysis. Okay? That's what you do. So you do the iterative process and you try to reach to a particular problem. So what I'm doing basically, I'm setting up an iterative problem. So I'm saying that let's have a un plus 1. Okay? And I'm defining un plus 1 as something which is f plus are you getting the point? Okay. So if, and this if is a big if, okay. So if this limit n goes to infinity, un exists, and I'm giving it a name u. If this exists, okay, then I can have a solution of this problem. Okay. What are you going to do? Just take the limit on both sides. So if this guy exists, then by taking the limit on both sides, what are you going to get? N goes to infinity, un plus 1 is f plus a un. Okay? And this would be, okay, both sides. We're going to have a limit here as well. And this would be same as f plus a. So since a is bounded actually, so I can take this limit inside of this bounded operator. So it's linear and bounded, so it's continuous. So for continuous maps, I can throw things inside it. So I can say that this is same as, okay, limit n goes to infinity, and from the continuity you get it, and hence you get a solution u is equal to f plus a. F plus a. So by this iterative process you can get what we call a solution. Now, what does this iterative process is allowing me to do it? This iterative process is making my life easier. How?
If there exists a sequence that approximates to u.
Exactly. So in other words, the key thing is sitting here. In other words, which is the sequence that approximates you, or which is the sequence which kind of gives you, which kind of converges actually. So I'm defining a sequence. I'm giving you a sequence. So the sequence is this. So take the first term, it's 0. So u1 is f, u2 is f plus af, and I'm defining u3 to be f plus af plus a square f, okay, and so on and so forth. Hence un is going to be some j equal to 0 to n, okay,
A power
that's
j,
n minus 1,
a power j,
f. How much time do we have? Let me just give you a quick hint of this lemma. I mean, if you just think about it, this lemma, and this lemma says this. So that E is a normed space. E is a normed space. So if F in E is such that U, which is j is equal to 0 to infinity, take the NF converges in E. Then what? This U satisfies your problem. U equal to F plus A. Okay? Now how does this result follows from our calculation? So let's reflect upon it again. So from where we began, we said that under what conditions, we can have a U which satisfies this equation. Okay. Then what we want to have a U which satisfies this equation. So I'm defining a sequence, UN plus AN plus 1 in such a way. So in other words, I'm taking this side of the problem, and using this I'm defining a sequence in each of the sequence. So UN plus 1 plus A. Okay. And I'm saying that this sequence is a convergent sequence. If this sequence is a convergent sequence, then I can take limit on both sides. So if I take limit on both sides, the boundedness and the linearity of the function allows me to take this limit inside the expression. And hence you get the limit of this sequence which satisfies this problem. But the question is, what is that sequence actually? So I'm giving you a sequence. I'm saying you take U0 to be 0, U1 to be F, U2 to be A plus AF, and U3 to be F plus AF plus AF square, and hence UN to be this actually. Now let me know that when this series is going to converge. Forget about the rest of things. When this series is going to converge, so it's a series of values going to converge.
When it's partial.
So its partial sums is convergent. So in other words, if these guys are convergent, then this series is also convergent. Are you getting the point? Yeah. So I'm saying now, let's put it in. So when you collect all this, I can collect all this discussion in the form of a lemma. So I'm saying that if I have a normed space E for which this series is convergent actually, okay, then the limit of this series, the sum roughly of this series, is going to satisfy the equation that you want actually. Are you getting the point? So hence, the problem of solving such an equation now is going to broken down to the convergence of this series. If you prove that this series is convergent, okay, this series is convergent, then you have a solution of your problem. Okay. And the real thing is that basically that for the convergence of this series, you have to kind of show that these partial sums of basically the series are convergent. Okay. So in other words, what does this lemma is telling you? That a sufficient condition for solving such an abstract problem in abstract space, normed space E, okay, you need convergence of this series. And this series is a series converging. So you see, what are the inputs of the series actually? So for the inputs you need the operator A, which you already have from the problem. And you need F actually, which you also already have from the problem. So you are using that F and A, you are creating a series. And you are saying that if this series is convergent, you have a solution of the problem. Okay? So, in the next discussion, what I am going to do, I am going to solve two problems. One integral equation problem, and second this perturbed Poisson equation problem. And I will say that for solving this equation, okay, what you essentially need, you need the convergence of this series. So if the series is convergent,
इसको शो करने के लिए फिर वही यूज करना पड़ेगा.
obviously you have to show this.
इसके ऊपर अगर नॉर्म अप्लाई करते हैं तो ये बाउंडेड है, तो उससे मेरे ख्याल में ये अप्रोक्सीमेट
इतनी आराम से नहीं हो सकता. You have to be very careful. You have to be very careful. So that's the key constraint. We're going to use this actually. So we're gonna carry on this next week. Okay. So in the next week